right, so the title of section 9.4 had odds and expected value. We talked about odds last class period and discussed kind of how that affected or was related to, I should say, probabilities. The other thing in this section is expected value. And expected value is thought of in this way. So if you have an experiment, and the experiment has outcomes A1, A2, all the way up to AN. So either it has outcomes heads or tails. It has outcomes, you roll the die, you get 1 through 6. Whatever the outcomes are, okay? And each of those has a probability, P1 through Pn. They each have their own probability. Now, a lot of the ones we've dealt with have had the same probabilities, right? If you roll the die, each one of their probabilities is 1/6. Okay, great. But there are some cases that we haven't had the same probabilities. We talked about a deck of cards, right? You're much more likely to get a face card than you are to get an ace. Right? You're much more likely to get a black than you are to get a diamond, specifically. So we don't always have those exact same things. But the expected value is actually found by taking each outcome times its probability. So when we're talking about expected value, we're talking about numerical outcomes. So I don't talk about the expected value of boy versus girl. That's not going to make sense in terms of the formula. Okay? But I can definitely talk about the expected value of rolling a die, because the die comes up with numerical values. So Hannah looks really confused. And all I'm doing is multiplying and adding. I multiply the value of the die. Let's use the die as an example. So if I have a die that's rolling as a 1 through 6, I multiply the value of the die. It has the probability of getting that value, which would be 1/6. So I multiply 1 times 1/6, 2 times 1/6, 3 times 1/6, and I do all the multiplications and I add them all together. And that would be the expected value of rolling a die. Okay. Now, that's fine, and that's all well and good with my die example, but I mean, it sort of seems strange because it's a one random event kind of one roll kind of thing. We're going to do some that don't have that kind of feel to it. Let's see what it's going to look like. But if you have an expected value in the end of 0, it means you have a fair game. Okay? So it means it's just as likely that I will win as you will win the game. So are games fair in a casino? No, that's why they have the big buildings and beautiful lights and stuff inside casinos, right? Because they're not fair games. They have to make more money or they will not be able to continue their operation. Agree? So most of the time when we're talking about gambling, we're not talking about a game that's what we consider to be a fair game. There are some games that are closer to fair than others, though. Okay, so let me talk about a roulette wheel. And I bring this into as an example, and I promise you at some point, somebody in my family is going to hear their name on a YouTube video and they're going to be like, oh, she talked about me, what? It's going to be crazy. But I bring up this example because in part B we're going to talk about my father-in-law, okay? And this is a for real thing. So on a roulette wheel, you actually have slots number 0, 0, you have the number 0, and you have numbers 1 through 36. One way to bet on a roulette wheel is to bet on a single number. Okay, so you can say, I believe when you spin that wheel, it's going on 2. And you put money down for it's going on 2. There's other ways to bet on a roulette wheel, but I want a real simple example to start with, okay? So what is the probability that if I that if I bet on a 2, that I win? One out of 38. Because I chose one of the different little slots, and there are 38 of them that I could have chosen. Are you with me? Do you guys know what a roulette wheel is? It's just a fancy spinner. It's a really big spinner, like for a game board. Okay? It's just got 38 different slots. 0, 0, 0, and 1 through 36. The slots are actually colored as well, and so you can bet colors of slot of the different on there too. And they aren't colored half red and half black, actually. The 0, 0, and the 0 are both colored in green, and then all the other numbers are colored every other in red. I think it's red and black, white and black, whatever it is, every other. So there's not a way to actually have a 1/2 probability with those numbers.
Where'd you get the 38?
So I actually didn't say 38. Sarah did. So where'd you get 38, Sarah?
Most of the slots must be right there on the top right. So 1 through 36, that's 36 slots. 0 takes a slot.
Oh,
Because I was just focusing on the 1 through 36. So I
Yeah.
was like, where did 38 come from?
Yeah, if we didn't have a 0, 0, and then 0 would be 36, and we've got two extra slots that are sort of special, and they're colored in green actually, because so you actually see your left wheel.
So the probability of each of these numbers is
Exactly. Yeah. Now, this is what my father-in-law does, sort of. I can simplify the example, but what my father-in-law does is a variety of this. So if you actually see a roulette wheel in a casino, and I make it sound like I've been to lots of casinos, which I haven't, but I've been to a couple, usually with my in-laws, they sort of do it like a video game. And they have a little set of money, and they go in and they play, and they kind of treat it almost like they were going to a movie. I mean, that's how much money they're going to spend, they're going to have a good time, sometimes they lose, but it's not an addiction issue or anything, so don't think that way, okay? But the roulette wheel actually shows the last however many numbers that have won. So it shows, that 10 times ago the number 12 came up, and 9 times ago the number 8 came up, and 7 times ago the number 4 came up, and so it shows the history of the roulette wheel, back so far, whatever. So here's what father-in-law does. He goes and he looks at the history, and he says, if it hasn't landed on, for example, 0, 0, that's not exactly how it does it, but we're pretending for a moment. If it hasn't landed on 0 in the past however many times, then that means it's more likely to land on 0, 0 when it's spent this time. This is what he thinks. And so he thinks then that he's going to actually have a better shot of winning because of the history of it, okay? So he will bet on the 0, 0. And if he bets one chip, and we're going to say one chip's worth $10, what is the expected value of his bet? And explain your answer. Okay, so it also tells me, I skipped over the fact that at the very beginning, if the ball lands on your number, then you receive 35 chips plus the chip you played. So you get 36 chips back. Okay, so you give them one chip. If you win, they give you 36 chips. They give you 36 because they give you one back that you started with. So 35 extra than you had to begin with. Yeah. Okay, so there's two things that can happen here, right? If I were doing a tree diagram, there's two things that can happen. I can win or I can lose, okay? So the first thing is, let's find the probabilities of winning. So what is the probability that I win? That is 1 out of 38, you got it. And what is the probability that I lose? 37 out of 38, and it has nothing to do with what has recently come up in history, correct? No, it does not at all. Now, the next thing I want to do is I want to figure out how much money I make if I win. So what do I make if I win? Well, how many chips? Let's say that first. I get 36 chips back, but actually one of them was mine to begin with, so I really only get 35 chips, right? That's how much I'll make, my profit, if you will. Then how much is each chip worth? $10. So how much do I make? $350, right? So this is a really good rate of return, right? If I could always win, I'd be very happy. I give you $10 and you give me back $360, so I make $350. Yay me. But I also have the probability that I lose money, and I'm going to say this in a positive way. How much do I, quote unquote, make if I lose? You're out $10. So in a positive sense of saying that, I actually am down negative 10. Of this 10. Okay, so this is a negative number. It is only 10. It is only 10, but it is 10, negative 10 in fact. Okay, so the negative is how much I make. It affects my net worth, how much I have in my pocket, by $10 in a negative way. Okay, everybody with me? Okay, so expected value, as we saw on the previous screen, what it does is it takes each outcome times the probability of that outcome. I have two outcomes, winning and losing. And each of those outcomes have a value associated with them. So my expected value is the outcome, that's $350 if I win, times the likelihood that that really happens, and that likelihood that that really happens is 1 out of 38. Plus the likelihood that I lose, which is a negative $10 outcome, putting my dollar signs off since I didn't on the first one. And the likelihood that that happens is 37 out of 38. Yes. Yes, that's exactly right. All right, so you're going to grab your calculators for me, and we're going to find some values. In fact, we're going to find the whole thing, right, all at once. So grab your calculator, tell it to do 350 times 1 out of 38, or divide by 38. And then either add or subtract the next value, the 10 times 37 out of 38. It's not looking like a very good 7. And this is money, so I want my answer reported to 2 decimal places since we're talking money. Okay.
Why do you have the money?
Because those are the 2 different options that we have, 2 different outcomes. Say 0 what again?
Like you said, it's the outcome.
Right, right. But these are outcomes. Well, it's not that the outcomes are equal chance. Well, let me explain it is. It has to do with whether or not the expected value is 0. Whether it's equally likely that you win money versus lose money. Yes. Now, what happens here, did we get a value? Let me talk about what you're saying here in just a second, but let me get the value for so we can talk about interest value. What did you get?
I got a negative.
Okay, can you write it in terms of money amount, so like a fraction or a decimal? What did you get?
I got 1894.
Really big.
And I got 1895.
Okay, so I'm going to take a look at your calculators.
I might have get it wrong.
You don't have a negative 10, you have a positive 10 up there. So in your case, you're going to make money either way. That's the game I was playing. How about you guys?
So that's when I got confused. I was like, that doesn't sound right.
Yeah, that doesn't sound right. Okay, so change that to a negative there, and then it should work out.
Negative 0.526.
Okay, so 5.3, that's money, right? Negative 0.53. Okay, so let's talk about what that means. Because we found something, but what does it mean? Okay? So this means...
Are we not supposed to have a negative sign on there?
No, it should have a negative. I'm sorry. I left it off. That's a negative for 10. It's not looking very good. But this means if I play a bunch of times, okay, lots of times, then, I mean, agreed. Sometimes I'm going to win and sometimes I'm going to lose. I mean, you know, if you play enough times, you're probably going to hit sometime or another. You're probably going to win at some point. All right, so if I play this enough times, then my average let's say gamble or whatever. My average gamble costs me 53 cents or $0.53. It costs me on average 53 cents to play the game. So if I win early on and I quit early on, then I'm probably going to be up for today. But if I have this mindset that I'm going to play until I win, I very well might play 500 times before I win and then have a whole bunch of money today. But over time, the expected value would be 53 cents. What that means from the casino's point of view is that on average, the people coming in and playing the roulette wheel in this way will end up leaving 53 cents on the table, which means that goes back into the profit for the company, right? And if it didn't, then of course then they wouldn't have the beautiful building that they have. So this is realistic, this is economics, right? So yeah. All right, so that's expected value. I want to take a look at expected value from a game show. So you guys familiar with Deal or No Deal? Okay. So in Deal or No Deal, we have contestants, and they're down to 2 cases. One of the cases is $250,000, and the other case is $1. And we want to know if we were the banker, what we should offer them as a deal. And you know how this works, right? At least roughly speaking, because probably if you've seen the show anyway. And they have these games actually at Chuck E. Cheese and at Lido, which is another form of Chuck E. Cheese.
How about at Dave & Buster's?
And Dave & Buster's, that sounds reasonable, yeah. So they've got this game, and this is how it's played, okay? And they do it with tickets or something like that if you see like the different arcades, if you will. All right, so if the game is fair and you're the banker, what do you offer the contestant as a deal? So, what is the likelihood that the $250,000 is in their case? a 1/2 probability of having $250,000 in their case. And they have a 1/2 probability, as in 1 out of 2 cases, of having a $1 in their case. Equally likely, right? So if we multiply 250,000 times 1/2 and 1 times 1/2, and we add these together, what do we get? So of course, they never offer 50 cents in the geek show. They're going to say something like 125,000, or they usually underscore it just a little bit to teach you. Right? Go ahead and just try your luck.
Didn't they do this on the game?
This is how they do the game. Sure
Really?
is. Yeah, and they do the same kinds of things whenever you watch. If you ever watch the Poker Channel and you see their probabilities pop up in the bottom screens, have you ever seen it before? It's been a long time since I've seen it, but they show you the probability that when they turn over certain cards that certain players are going to win. You know, what the likelihood is that they're going to win, and they do it with probabilities. They actually usually change it in percentages of that. They do that too. Yeah, they do.
So that's what he's really doing, right? The dark screen.
Yeah, but I suspect he's actually doing it with some fancy calculator that he doesn't know how to use. But that was my guess. So. All right, we're going to do another one. All right, there's a cartoon at the beginning of your section. I think I'm sure it's still in this edition of the book, but in the cartoon at the beginning of the section, it was the whole edition. Actually, I think it is. I think I checked it to make sure. The odds against winning the lottery were 55 million to 1. Good luck. What is the probability then of winning the lottery? That's a different question, right? This incorporates odds and probability within the same problem. So the odds are 55 million to 1. So what's the probability? There you go. You're just off by how you're thinking about the number. Say that louder, Sarah. Okay. So we've got a 1 out of something chance, and that number is the other number you just told me. 55 million and 1. Okay. So because remember, when you talk about odds, you're talking about the number of people who win versus the number of people who lose. Okay. 55 million lose. 1 wins, which means there's a total of 55 million and 1 person. Okay, that's where that we're exact. Okay, we're an exact representation. 55 million and 1 people play, 1 person wins. Yes?
On the last slide, will we just say that the game is fair if the offering that?
Yes. Yeah. This is already answered.
So a game is fair
when there's an equal probability of winning one versus another. Fair is not the best descriptor of this game because we can't lose money in this game, right? Because we either win a little bit or we win a whole lot. So fair would be the halfway point. Yeah. All right, so here we've got a grand prize. The grand prize is $13,567,290, and a ticket costs $1. And the question is the game fair? So just like with our last game, we either win or we lose, right? Like with the roulette wheel. So what is the probability? Well, let's just do this. What is the net gain if you win? If you win, how much money do you win? $2.89, right? Because you had to pay $1 to play, and so you actually have one less than money to give you back because you paid $1 into the system. Now, how likely is it that you actually win? That is, what is the probability that you win? That's the first number we did on part A. It's a 1 out of 55 million and 1 chance. What's that? Are you going to say?
Yeah, I was thinking this was a completely different one, like grand prize or something else, not grand prize of the lottery.
Gotcha. Yeah. Grand prize for the lottery. What's that? Yep, this is expected value, exactly. It is E equals, you're right. I'm going to run out of space, so I'm going to add it down here. This is probably winning, but we also have a chance that we do not win. If we do not win, what is our net gain or loss? What's the deal to our worth? -1. It cost me $1 to play. And this is what happens to people that lottery, they're down here. Right? Because what's the probability that they lose? 55 million out of 55 million and 1. So in other words, nearly all of the time. Okay? You're more likely to get struck by lightning than to win the lottery. You've heard that before? It's actually struck by lightning several times actually in the lottery, but I don't know the exact number. All right, so your calculator, if you multiply this out, it's going to tell you, and I'm going to save you the trouble, just so you know. If you actually multiply this out, you will end up getting that it is negative, big surprise, 75 cents. So is the game fair? No, the game is not fair. It's a money-making scheme for whoever's doing the lottery. No, not fair. So again, let me reiterate, because I want to let you hear it one more time and have it recorded one more time. What this means is that you play the lottery often, like lots of times. Over time, the average expected value is that you lose 75 cents out of every dollar you play. Okay. So are you going to win? Maybe. I mean, there's a chance. Obviously, somebody is going to win in this situation. They're going to win this much money. Eventually, somebody wins these lotteries. But, you know, it's not going to be used. Don't like it. Okay. It's just not real likely going to happen.
I'm still the fair thing. Like on the last one.
Yeah, the last one that I did, being fair, is a weird question. The ones we are going to deal with, and your work's going to deal with being fair, have this connotation. So
right.
a negative or a positive gives you fair.
Yeah. We just said game is fair, expected value is 0. But on the last, on the deal or no deal,
Yeah.
it's fair because it's the middle between when they're going to.
Because we're not playing any money to pay any money to play. Okay. Yes.
Okay. That's
Yes.
because this one you're not losing.
Right. And one way you could think about it on this particular problem is what would be fair instead of the contestant? What would be fair to the banker? Right? The banker either gives away 125,000 and some change, or he keeps, you know, 2.5 or $250,000. I think you can think about it from the perspective of the banker. It helps in that moment.
I would take that one.
You would take that one? I would take the deal too.
It'd be stupid.
Okay, this actually should hit a little bit home to you because lotteries do this a lot and you need to actually see what they're doing when they do it. So as with many state lotteries, the proceeds are often said to benefit education. You heard that before?
Yeah.
Okay, so whether it is or it isn't, that's not the issue under discussion here. What I want you to see is this. Under these conditions, if the proceeds do in fact benefit education and 1 million tickets are sold, what is the expected value generated for education from the lottery sales? Okay, so the person is how we looked at it on Part B. The person is expected to lose 75 cents out of every dollar. But that means who gets the 75 cents according to this problem? Education. So education's perspective is that this is not a negative 0.75, it's actually a positive 0.75. And again, you guys didn't put the calculator in there, but I will tell you that the next numbers were 3322, which I realize is not a dollar amount. But I'm going to take this number and I'm going to multiply it by 1 million because there were 1 million tickets sold. Okay?
What's this number? Expected value again?
Yes, this is expected value of the number of tickets. So we're taking the expected value, we found the expected value, right? The expected value for one ticket. We want to do it now for the 1 million tickets. So we're taking the 1 million tickets that were sold, because it says 1 million tickets sold, and we're taking the cost of that one single expected return on that one ticket, and we're multiplying it by the number of tickets. So this is Not the same expected value we were talking about before, but this is the expected value of my million tickets.
So the reason it's only those two is because the one option.
Yes.
Just for million tickets.
Yeah, I mean, we could take this if you wanted to, Sarah. We could go back and we could multiply a million tickets by this and a million tickets by this, and we could go and do that.
No, yeah, I'm just saying, like,
but, yeah.
as far as the formula, like why it's still the same formula as this. One option.
Right.
We have A, B, and C.
Right. That's true, yes. And the issue, again, is that we already actually found the expected value. We're just taking that expected value and we're extrapolating what can happen. All right, so we have this 75 cents times this 1 million, and if we multiply this out, I end up getting 753. I don't know if I've got my numbers right now that I'm reading this, because my numbers don't match up here. But let's imagine for a moment if this is correct, we'd have 322. I may be off, but I'm not going to make you guys the same. And I just didn't put my first numbers right. The two numbers I think would actually match. My first number does not match my second number. If the first number is right, then this is the second number. Okay. All right, so this would mean that education benefits by having an extra $750,000, give or take, into their budget, right? But the deal is, that's not really what happened. What really happened is everybody lost who played, right? All 1 million people lost. Or one of those 1 million people won. Are you guys following me? Okay. So what really happened is either option 1 is everyone loses. That is everyone who played. Not education, but everyone who plays loses. If everyone loses, well, each of them paid $1 to play. And there were, 1 million tickets sold. Which means how much does education win if nobody wins? $1 million. Education got $1 million. Okay. So one option is education is up 1 million because of the lottery. The second option is that the one person won. Okay, now let's talk about this. If one person won, how many lost? So 999,999 lost. So the 900,999, all those people still gave you $1, and so you still made $999,999 from those people, right? So this right here generated $999,999. Okay, those people still paid in the money and they didn't get anything for their money. Except they put a smile on their face and said, right? Or not. And then our one person who won, and they paid $1 to play, but what?
They won 13,000.
Not 13,000, 13 million. They won 13 million. 567,289 because they paid $1 to play, dollars. And this is negative. It's actually why I did red. Okay, the negative, because I actually, from education standpoint, that's not a positive plus value, right? That's a bad thing, because that means less money that they got. And the kicker is that this number was 999,000. This number's 13 million. And if you subtract these, it means that this general fund or whatever called the lottery is actually negative.